For most planets, the solar system follows a pattern. They spin in roughly the same way, keep familiar seasons, and hold to a shape that feels orderly and expected. But Uranus does not. It rolls through space on its side, lives through decades of daylight and darkness, and carries one of the strangest magnetic fields in the solar system. Tonight, this quiet blue world reveals why Uranus seems to break all the rules. If this is the kind of deep space journey enjoyed here, please like the video, subscribe to the channel, and settle in, far from the busy inner reaches of the solar system. Uranus moves through a broad and quiet region where the Sun has already become a small and distant source of light. It is the 7th planet from the Sun, beyond the orbit of Saturn and well inside the still more remote path of Neptune. At this distance, the familiar pattern of the planetary system begins to feel stretched and spare. The gaps between worlds are wider, the pace of motion is slower, and sunlight arrives with only a small fraction of the strength it has near Earth. Uranus belongs to this outer realm in a complete way. It is not a border object between inner and outer regions, but a true member of the deep planetary frontier, where cold, darkness, and long timescales shape nearly everything that can be seen and measured. Its average distance from the Sun is about 2.9 billion kilometers, or about 19 times the distance between Earth and the Sun. That single fact changes the character of the planet more than any simple image can show. Sunlight needs about 2 hours and 40 minutes to cross the space between the Sun and Uranus. By the time that light reaches the planet, it has spread thinly across a vast sphere of space, so the daylight there is far weaker than daylight on Earth. Even at noon, the Sun would not dominate the sky in the same way. It would still shine clearly, but as a much smaller and less forceful presence, one that rules by persistence rather than intensity. This great distance also means that Uranus completes one trip around the Sun only once in about 84 Earth years. A single Uranian year is therefore close to the span of a human life. The outer solar system gives a sense of scale that is different from the inner planetary neighborhood. Near Mercury, Venus, Earth, and Mars, the Sun remains central in a vivid and immediate way, and the intervals between planets, though enormous by human standards, still feel tied closely to one bright center. Out near Uranus, that relationship loosens. The Sun still governs every orbit, but it does so across distances so large that motion seems patient and almost reserved. The planet does not rush through its year. It advances with a steadiness that reflects the slow rhythm of its path. Its orbit is nearly circular when compared with the more stretched paths seen elsewhere in the solar system, and it remains close to the common planetary plane as it circles the Sun in outward position. Uranus seems unusual because it is so distant. In its basic path around the Sun, however, it remains a regular planet, held by the same gravity and moving under the same broad order as the rest. Because it is so far away, Uranus also occupies a quieter place in human awareness than Jupiter or Saturn. It is dim, restrained, and difficult to read from Earth without instruments. Its remoteness is not merely a matter of kilometers. It is part of why the planet feels less familiar. Even now, the world exists in the same solar system as Earth, yet distance keeps it visually modest. Nothing about its appearance from afar suggests urgency. It asks for patient observation, careful measurement, and respect for faint evidence. In this sense, Uranus teaches a simple outer solar system lesson. Important worlds are not always bright worlds. Some of them reveal their nature only when attention adjusts to slowness, subtlety, and scale. In this remote setting, Uranus is often grouped with Neptune as an ice giant. The term does not mean that the planet is a frozen solid object with a hard icy surface. Instead, it marks Uranus as part of a category distinct from the larger gas giants Jupiter and Saturn. Uranus is about 4 times wider than Earth and is the third largest planet in the solar system by diameter, yet it is still much smaller than Jupiter and Saturn. The name ice giant reflects the importance of substances such as water, ammonia, and methane in the planet's overall makeup, especially when compared with the composition of the larger giant planets. From this outer vantage alone, Uranus already stands apart as a world that shares the giant planet family resemblance, while also occupying its own place within it. The cold of Uranus begins in this setting. The outer solar system receives little solar energy, and Uranus moves within that sparse reservoir of light for the entirety of its long year. Its environment is therefore defined by scarcity. Warmth from the sun is limited. Illumination is limited. Change driven directly by solar heating unfolds slowly. The whole planetary system around Uranus exists under these conditions of reduced energy input from the start. Seen from far away, the planet appears calm partly because distance itself creates a calmer visual world. Bright contrasts soften. Colour seems restrained. Motion becomes hard to detect without long observation. So the first truth about Uranus is not a detail of weather or a puzzle of internal physics, but location. It lives in a remote band of the solar system where the sun is diminished by distance, where 1 year lasts 84 Earth years, and where the ordinary assumptions formed near Earth no longer fit very well. To see Uranus clearly, observation begins by accepting that remoteness is not an incidental background condition. It is the governing frame. The planet's faintness, slowness, cold, and reserve all begin here, in the wide dark between Saturn and Neptune, under a weak sun that still holds the planet firmly, but from very far away. In that immense spacing, Uranus takes its place as one of the solar system's major worlds, quiet in appearance, exact in motion, and shaped from the outset by distance itself. Uranus presents one of the strangest orientations in the solar system. Most planets spin in a way that keeps their poles more or less upright relative to the flat sheet in which the planets orbit the Sun. Earth is tilted, but only moderately. Jupiter is only slightly tilted. Saturn also leans, but still keeps a clear distinction between an upright planet and the path of its orbit. Uranus does something different. Its axis, the imaginary line running through its north and south poles, is tilted by about 98 degrees. In practical terms, this means the planet rotates almost on its side. Instead of spinning like a top that leans a little, Uranus turns more like a barrel rolling around the sun while still keeping its own steady daily spin. This sideways posture changes the meaning of day and season. Uranus still rotates relatively quickly. One turn takes about 17 hours. So the planet does have a regular cycle of rotation, and the sun still rises and sets in some regions under some seasonal conditions. But the broader pattern of light across the world is governed less by the short daily spin than by the long, slow progress of the planet around the sun. Because Uranus needs about 84 Earth years to complete one orbit. Each major season lasts for about 21 Earth years. That alone makes its climate pattern unusual. The severe tilt makes it stranger still. At one part of the orbit, one pole points almost directly toward the sun. When this happens, that hemisphere enters a period of prolonged summer illumination, while the opposite hemisphere turns away into prolonged winter darkness. This is not a brief polar season of the kind seen on Earth. Near the poles of Uranus, the effect lasts for decades. Observations and orbital geometry show that each pole can spend about 42 Earth years in continuous sunlight, followed by about 42 Earth years in darkness. The light is weak because Uranus is so far from the Sun, but the persistence of that light is extraordinary. In one half of the long Uranian year, sunlight lingers without a normal night. In the other half, it does not arrive at all. This arrangement gives Uranus a seasonal structure that feels almost inverted when compared with the more familiar planets. On Earth, the equator receives the most consistent sunlight over a year, and the poles experience the strongest seasonal contrast. On Uranus, the poles at some times receive more direct seasonal attention from the Sun than the equatorial regions do. Near solstice, when one pole faces the Sun most directly, the polar region becomes the part of the planet most fully turned toward daylight. The equatorial zone, by contrast, lies around the side of the planet and can pass through a more unusual cycle of light and darkness produced by the combined effects of the sideways axis and the daily rotation. As Uranus continues along its orbit, the geometry slowly changes. The planet reaches an equinox when its axis points sideways relative to the Sun rather than toward or away from it. At that stage, the Sun shines more directly over the equatorial regions, and day and night become more evenly shared across much of the globe. Even this more balanced phase unfolds slowly by Earth standards. Nothing about Uranus changes quickly on the scale of a human season. The shift from one lighting regime to another stretches across years and then across decades. The planet therefore does not merely have long seasons, it lives in them deeply, with sunlight patterns that remain in place long enough to shape entire eras of atmospheric response. Its rotation itself is also unusual in direction. Uranus spins in what is often described as a retrograde sense, a term used when a planet rotates in the opposite direction from most planets. Venus also shows retrograde rotation, but Uranus differs because its extreme tilt makes the idea of direction more difficult to picture in everyday terms. What matters most in the visible seasonal pattern is that the axis is not slightly misaligned or modestly inclined. It is dramatically displaced. The poles do not simply lean toward and away from the Sun during the year, they take turns almost facing it outright. This is one reason Uranus seems to break rules even when it still obeys the same gravitational laws as every other planet. The solar system contains tilted planets, fast planets, slow planets, and giant planets. Uranus combines these features in a way that produces a rare balance of order and strangeness. Its orbit remains stable, its rotation remains regular. Yet the angle between those two motions is so extreme that the planet presents sunlight to itself in a pattern unlike that of any other major planet. The result is not chaos. It is a different kind of planetary order, one built around a geometry that appears almost improbable but persists with perfect consistency over time. The origin of this tilt remains an active scientific question. Long-standing models have suggested that Uranus may have experienced one or more giant collisions early in its history, with impacts large enough to knock the planet onto its side. More recent work has also explored whether gravitational interactions involving a large former moon could have tilted the planet over long periods of time. Observations strongly support the fact of the tilt itself and the seasonal consequences that follow from it. It remains less certain which early event or sequence of events produces the present arrangement. In this outer view of Uranus, the most secure statement is simple. The planet now exists in a stable sideways orientation, and that orientation governs the pattern of sunlight across its world. Seen from afar, Uranus is therefore not merely distant and cold, it is also geometrically transformed. The Sun reaches it weekly, but it reaches different parts of the planet in an astonishing way. Decades of day and decades of night are not passing curiosities. They are basic conditions of life on Uranus as a physical world. Every long season, every polar interval of light or darkness, and every slow transition between them begins with the same fundamental fact: the planet rotates almost on its side as it travels through the outer solar system. Around Uranus lies an invisible outer shell shaped by magnetism. This shell is called a magnetosphere, a region of space where the planet's magnetic field helps control the motion of charged particles. Every giant planet has such a region, but Uranus does not arrange its magnetic surroundings in the expected way. At Jupiter and Saturn, the magnetic field and the spin of the planet line up closely enough that the larger magnetic structure keeps a recognizable symmetry. Uranus does not offer that kind of balance. Its magnetic environment is irregular from the start, and that irregularity begins with the basic geometry of the field itself. Voyager 2 revealed that the main magnetic field of Uranus is steeply tilted relative to the planet's rotation axis by about 59 degrees, and that the magnetic field is also offset from the planet's center by about 1/3 of the planet's radius. This means the field is not routed neatly through the middle of the world. It sits askew and off-center, giving the planet a magnetic shape unlike any earlier one measured up close in the solar system. That strange arrangement matters because a magnetosphere is not a fixed sculpture. It is a moving boundary between the planet and the solar wind, the constant flow of charged particles streaming outward from the Sun. At Uranus, the solar wind is weaker than it is closer to the Sun, but it still presses on the planet's magnetic field and helps shape the outer magnetic cavity. Because Uranus itself rotates in about 17 hours while the magnetic field is both tilted and displaced, the surrounding magnetic envelope does not simply sit in one steady orientation. It lurches and twists through space as the planet turns. A place within the magnetic region that faces the solar wind at one moment may rotate into a very different position only hours later. The result is a magnetic environment that changes its geometry over each planetary day in a far more dramatic way than the magnetospheres of the more familiar giant planets. The visual consequence, if the invisible could be seen, would not be a smooth and dignified shell centered cleanly on the planet. It would be an uneven envelope with a head turned toward the Sun, a long tail drawn away from it, and an internal structure that keeps shifting because the field itself is skewed. Magnetic poles do not remain in a simple relation to the Sun. Regions where charged particles can become trapped do not remain arranged in a stable, planet-centered way. The whole system behaves like a rotating machine whose main axis, inner field, and incoming solar flow fail to agree with one another. Uranus still obeys the same physical rules as other planets. The solar wind presses inward, the magnetic field pushes outward, and the two produce a cavity in space. Yet the shape of that cavity becomes unusually asymmetric because the underlying magnetic source is itself unusually asymmetric. This is one reason Uranus has long interested planetary scientists as more than a curiosity. Its magnetosphere is not simply tilted. It tests ideas about how planetary magnetic fields are generated and how they behave when they're not anchored in a near-central, near-aligned way. At Earth, the field is often described in simple terms, as though a bar magnet sat close to the center of the planet. That image is only an approximation even there, but it is much less misleading than it would be at Uranus. The Uranian field suggests that the internal region producing magnetism may operate in a shell rather than deep in a centered core, though the exact internal process remains uncertain. What is firmly observed is the external result, a magnetic structure whose poles, trapped particles, and surrounding boundaries are all arranged in a distinctly off-balance manner. The scale of this surrounding magnetic domain is large even when compressed by the solar wind. During the Voyager 2 encounter, the main boundary where the pressure of the solar wind balances the planetary field lay many Uranus radii from the planet, and farther out still, the spacecraft crossed the bow shock, the outer disturbance where the incoming solar wind slows abruptly before flowing around the magnetosphere. Even these immense distances do not make the region simple. Charged particles can be stored within it, guided along field lines, accelerated, or lost, depending on how the field rotates into the solar wind and how conditions change outside the system. Space around Uranus is therefore not empty in any practical sense. It is structured, partitioned, and shaped by forces that cannot be seen directly, but leave clear signatures in instruments. For many years, scientists viewed the Voyager 2 flyby as the defining picture of Uranus and its magnetosphere, because it remains the only spacecraft visit to the planet. That encounter transformed knowledge of Uranus, but it also came at one particular moment under one set of solar wind conditions. More recent analysis indicates that Voyager 2 may have arrived during an unusually compressed state of the magnetosphere, created by exceptionally strong solar wind pressure. If so, some earlier impressions of a sparse plasma environment and an oddly extreme magnetic setting may reflect a rare moment rather than the planet's typical condition. This does not erase the fundamental strangeness of Uranus. The field is still highly tilted and offset. The outer magnetic shell is still highly asymmetric. But it does mean that the exact size and internal state of the magnetic environment may vary more, and may usually be less compressed than the single historic flyby first suggested. So in the space immediately around Uranus, one finds neither a calm spherical envelope nor a steady magnetic umbrella. One finds a shifting wand, off-center structure that rotates with a sideways planet and meets the solar wind at changing angles through the day. It is broad, dynamic, and difficult to summarize in any simple picture. The field does protect and organize a region around the planet, but it does so with a geometry that appears bent away from expectation. Uranus seems, even here, to break a rule, though the deeper truth is that it reveals how wide the rules of planetary physics really are. A magnetosphere does not have to be neat to be real. At Uranus, it only has to persist, rotate, and hold its charged surroundings together in a shape that is unmistakably its own. At the edge of Uranus, the magnetic shell does more than bend the path of charged particles. It also creates brief regions of light. These are auroras, luminous emissions that appear when energetic particles move along magnetic field lines and enter the uppermost part of a planet's atmosphere. There, they collide with atoms and molecules, transferring energy that is later released as light. The basic process is familiar from Earth, Jupiter, and Saturn. At Uranus, however, the geometry is far less orderly. Because the magnetic field is both steeply tilted and offset from the planet's center, the places where incoming particles are guided downward do not remain arranged in a simple, steady pattern around the rotational poles. Auroral activity at Uranus belongs to a magnetic system that is already skewed before the particles even begin their descent. The light produced by these events is not obvious from ordinary viewing. Uranus is distant, dim, and difficult to study. Its auroras are faint compared with the powerful displays seen at Jupiter. They have been detected mainly through ultraviolet observations, including work with the Hubble Space Telescope, rather than by direct visible inspection from Earth. This means that the outer edge of Uranus reveals itself not through grand luminous curtains, but through restrained signs that require precise instruments. Even so, the underlying physics is clear. Charged particles from the solar wind and particles already moving within the planet's own magnetic environment can be accelerated and guided toward the atmosphere. When they arrive, they excite atmospheric gases and produce measurable emissions that mark the points where magnetism and matter briefly meet. On a more upright planet, auroras tend to gather around magnetic polar regions in a relatively understandable way. The field lines converge, particles follow them inward, and the auroral zones maintain a broad connection to the shape of the planet below. Uranus weakens that familiar picture. The magnetic poles are not located in a straightforward alignment with the spin poles. The whole magnetic structure rotates through space with a strange relation to the Sun, and so the access routes by which particles enter the atmosphere can change their orientation over the course of a single Uranian day. The auroras are therefore linked not just to the presence of a magnetic field, but to the changing posture of a lopsided one. In practical terms, the outer edge of Uranus is a place where the invisible architecture of the field decides where the brief flashes of energy will appear. Observations over the years show that these auroral events can be highly variable. Some detections occur when the solar wind appears to deliver stronger pressure or sharper disturbances to the magnetosphere. In such moments, the outer magnetic boundary is compressed, currents strengthen, and the system becomes more effective at driving particles inward. Uranus responds with ultraviolet brightenings that indicate auroral activity in the upper atmosphere. At other times, the signals are weaker or harder to isolate. This does not mean the process stops. It means the magnetosphere of Uranus is a dynamic gateway rather than a constant beacon. The planet's auroras are episodic, shaped by the changing state of the solar wind and by the internal geometry of a magnetic field that rarely presents the same face twice. There is also a seasonal aspect to how this outer region is viewed and understood, because Uranus spins on its side. The orientation of the magnetosphere relative to the Sun changes dramatically over the long Uranian year. Around solstice, one rotational pole leans more directly toward the Sun, while around equinox the geometry becomes different again. These shifts alter how solar wind energy couples to the magnetosphere and may influence where and how auroral signatures appear. Observations indicate that the auroras of Uranus can look different at different orbital phases, though the limited number of close measurements means the full pattern remains incomplete. Scientists know that the planet's seasonal geometry matters. It remains uncertain exactly how the most detailed long-term auroral behavior changes across an entire Uranian year, because no spacecraft has stayed at the planet long enough to watch the full cycle unfold directly. Even with those limits, the outer meaning of the auroras is important. They show that Uranus is not simply a quiet blue world with a strange tilt. It is an active participant in the flow of solar energy through the outer solar system. The Sun is weak at that distance, but its influence still arrives in the form of the solar wind, and Uranus still responds. The auroras trace that response in light. They show where external plasma, internal magnetic structure, and the planet's upper atmospheric edge briefly join in a single event. In that sense, the auroras are not surface weather. They are the visible signature of a contact zone between space and planet. This contact zone is especially revealing at Uranus, because almost every part of the arrangement departs from easy expectation. The planet is remote, its magnetic field is tilted and off-center, its rotation is rapid, yet its seasons are decades long. Its auroras are faint, intermittent, and strongly tied to geometry that is difficult to picture. Yet none of this makes the process obscure in principle. Particles move, Fields guide them. Gases are excited. Light appears. The strangeness comes from the arrangement, not from the physical law. Uranus keeps the same fundamental rules of magnetism and charged motion seen elsewhere in the solar system. What changes is the shape in which those rules are expressed. So the outermost active edge of Uranus is neither empty nor still. It is a boundary where energy arrives from the Sun, where the magnetic field reshapes that energy into organized pathways, and where the uppermost atmospheric gases answer with delicate emissions. The auroras of Uranus are modest in brightness, but they are exact in meaning. They reveal a world whose outer shell is alive with magnetic interaction, even under weak sunlight and at immense distance from the Sun. In the dark region around the planet, these brief ultraviolet glows serve as one of the clearest signs that Uranus remains connected to the wider solar system, not by brightness or heat, but by invisible forces that reach across billions of kilometers and still find the planet's tilted, rotating, off-balance magnetic gate. Beyond the tilted magnetic shell and beyond the brief auroral edge, Uranus is accompanied by a wide family of moons. They circle the planet at different distances and with different histories, forming a system that is quieter in appearance than the busy moon systems of Jupiter or Saturn, yet still rich in variety. Uranus is known to have 28 moons. Some are large enough to show complex geological stories on their surfaces. Others are small, dark, and faint, detected only through careful observation. Taken together, they make Uranus more than a solitary blue planet. They give it a surrounding realm of secondary worlds, each one moving under the pull of the same remote giant in the cold outer solar system. The first impression of this moon system is restraint. Nothing here resembles the huge and crowded populations around Jupiter or Saturn, where many large moons compete for attention, and where volcanic or icy activity announces itself strongly. The Uranian moons are more subdued. Their light is weak. Their colours are muted. Their motions are regular but slow enough, from a human point of view, to seem almost still. Yet this restraint is only outward. The moon system preserves a long record of impacts, fractures, resurfacing, and orbital history. It also preserves a useful order. Far from the planet lie small outer moons whose exact composition remains uncertain, and whose dimness makes them difficult to study in detail. Closer in, but still well outside the narrow ring zone, lie the 5 major moons that define the main architecture of the Uranian satellite system: Miranda, Ariel, Umbriel, Titania, and Oberon. The most distant known moons of Uranus are small and irregular. They are not the rounded, dominant companions seen among the major moons. They are faint objects, likely captured bodies rather than moons that formed neatly within a smooth disk around the planet. Their remote orbits and weak brightness suggest a different origin story from that of the larger inner family. They are part of the Uranian system now, held by the planet's gravity. But they give the impression of a loose outer frontier rather than a carefully built central structure. Very little can be said about them with the confidence available for the major moons, because they remain so difficult to observe. Even so, their presence shows that Uranus does not end with its visible globe or with its rings. Its influence extends outward into a broad and sparsely populated moon realm, where capture and long-term gravitational stability likely play an important role. Inside this faint outer fringe, the 5 major moons establish the character of the system more clearly. They are not equal in size or appearance, but they share broad traits. All are thought to contain roughly similar mixtures of water ice and rock. All are cold, airless bodies. All were observed much more closely only once, during the Voyager 2 flyby in the 1980s. That encounter remains the foundation of most direct knowledge about their surfaces. Even now, decades later, the Uranian moons are known in far less detail than the larger icy moons of Jupiter and Saturn. This limited record gives them a particular scientific quality. They are visible enough to reveal complexity, but still remote enough that many details remain unfinished. Oberon, the outermost of the 5 major moons, marks the broad outer boundary of this principal moon family. It is one of the 2 largest moons of Uranus, and one of the first to be discovered. Its surface is old and heavily cratered, with relatively little sign that later processes have erased the marks of impacts. In this way, Oberon keeps a long memory. Craters remain clear, and the surface appears comparatively stable over vast stretches of time. Dark material is seen on some crater floors, and at least one large mountain rises from the battered crust. Oberon gives the sense of an ancient outer companion that has spent most of its existence preserving rather than renewing its face. Titania, the largest moon of Uranus, orbits inward of Oberon. It is also ancient, but it does not appear as static. Voyager images show faults and long surface features that indicate geological activity in the past. Its crust seems to have responded to internal change, perhaps expansion as interior materials shifted or cooled. Titania therefore looks like a moon that keeps the marks of both impact and internal movement. It does not display present activity in any confirmed direct way, but its surface records a history that is more than passive survival. Among the major moons, it stands as the largest and perhaps one of the most significant for understanding how a medium-sized icy body can change over time while circling a distant ice giant. Umbriel is darker than the others and gives a more subdued impression. It is the darkest of the large Uranian moons and one of the most heavily cratered. Its ancient surface appears to have undergone little resurfacing compared with brighter moons such as Ariel. A strange bright ring-like feature stands out on one part of its face, an isolated mark against an otherwise dark and old landscape. The reason for Umbriel's darkening remains uncertain. What can be said is that its surface has kept an old, quiet appearance, as if it has spent much of solar system history avoiding the internal renewal that might have refreshed it. Ariel contrasts with Umbriel. It has the brightest surface among the major moons and shows signs of more extensive resurfacing. Valleys, scarps, and long intersecting features cut across its icy crust. The relative lack of very large craters suggests that later processes have altered or renewed wide parts of the surface. Of all the major moons, Ariel often appears the most geologically youthful in outward expression. Though youthful here still means ancient on a human timescale, it simply means that more of its history remains written in tectonic patterns and surface change rather than only in impact scars. Miranda, though the smallest of the 5 major moons, is often the most visually startling. Its surface is broken into regions that look mismatched, with giant fault canyons, terraced structures, and landscapes that seem patched together from different geological episodes. It is a small moon with a remarkably varied face. This makes Miranda important not because it dominates the system in size, but because it shows how even a modest icy moon can record a complicated internal and orbital past. This outer moon realm around Uranus is therefore not uniform. It begins with faint distant bodies, likely captured and still poorly known, and then gathers inward into 5 major moons that each preserve a different balance of ice, rock, impact history, and internal change. Some are dark, some bright, some look old almost everywhere, while others show stronger signs of resurfacing and fracture. All move in the calm, weak sunlight of the outer solar system, carrying their histories around a planet that itself turns on its side. Together they form the first true family encountered around Uranus, a set of cold companions that do not shout their differences, but reveal them slowly through cratered plains, bright scars, dark crusts, and ancient ice that has not lived one single story. Inside the broader realm of the major moons, the Uranian system tightens suddenly. Here the wide spacing of the outer companions gives way to a crowded inner family of small moons packed close to the planet and close to one another. These bodies all orbit inside Miranda, and most are irregular in shape rather than round. They are too small for their own gravity to pull them into spheres, so they remain lumpy and uneven. Voyager 2 discovered many of them during its brief pass through the Uranian system, and later observations from the Hubble Space Telescope added more. Together they reveal that the space near Uranus is not empty between planet and major moon. It is filled with a delicate architecture of minor bodies whose orbits sit close together in a narrow zone. This inner family includes Cordelia, Ophelia, Bianca, Cressida, Desdemona, Juliet, Portia, Rosalind, Cupid, Belinda, Perdita, Puck, and Mab, with recent Webb observations also identifying an additional tiny moon in the same general region. The names matter less than the pattern they form. Almost all are dark, small, and faint. Their surfaces are thought to be mixtures of ice and rock, darkened by space weathering and by carbon-rich material. Seen together, they do not resemble a procession of major worlds. They look instead like survivors in a compact system, each one occupying a narrow path where even modest gravitational nudges from neighbours can matter over long periods of time. Puck is the largest of the long-recognised inner moons, and in many ways it marks the outer edge of this close-packed family. It is still small compared with the major moons, but it is large enough to stand out among the minor satellites. Its surface, as seen by Voyager 2, is dark and cratered, with no sign of present activity. Farther inward lies Mab, a much smaller moon that has drawn interest because of its association with a faint dusty ring. Mab is not important for its size. It is important because it shows that small moons near Uranus are not only orbiting bodies, they may also supply material to the nearby dust environment through impacts and slow loss of surface particles. Deeper into this region, the moons become more crowded. Perdita, Belinda, Cupid, Rosalind, Portia, Juliet, Desdemona, Cressida, Bianca, Ophelia, and Cordelia occupy a surprisingly narrow band. Several of these belong to what scientists often call the Portia group, a cluster of moons with similar dark surfaces and closely spaced orbits. Their arrangement is one of the most tightly packed among the regular moon systems of the giant planets. This matters because gravity does not need immediate collision to shape such a system. Repeated small tugs, orbital resonances, and long accumulations of change can slowly alter paths. Numerical studies indicate that parts of the inner Uranian moon system may be dynamically unstable, on timescales far shorter than the age of the solar system. In plain terms, the present arrangement may not last unchanged forever. Some moons may eventually collide, merge, or break apart, even though on human timescales the whole system appears calm and orderly. That contrast defines the region. At first glance it seems quiet. The moons move on nearly circular paths close to the planet's equatorial plane. They follow Uranus in the same broad prograde direction as the major regular moons. Nothing in simple images suggests unrest. Yet the structure is so compact that order has to be maintained within narrow margins. The inner Uranian system therefore resembles a balanced arrangement more than a permanent one, It is orderly at the moment of observation, but likely evolves through episodes of collision and renewal over geological time. This idea helps explain why the region contains both moons and nearby dust in such close association. A crowded system of fragile, dark bodies naturally produces debris when impacts occur. 2 moons in this region, Cordelia and Ophelia, illustrate the architecture especially well. They are known as shepherd moons, meaning that their gravity helps confine nearby ring particles and keep a narrow ring from spreading away. Cordelia lies just inward of the bright epsilon ring, while Ophelia lies just outward of it. Their role shows that even very small moons can shape the structure of the Uranian system. They do not dominate by mass. They guide by position. A moon does not need to be large to matter when it sits close to loose material, moving on nearly the same path. In this inner realm, location is a form of power. The small sizes of these moons also mean that very little is known about their individual geology. Most are seen only as dark bodies with measured brightness, approximate shape, and orbital motion. Only Puck receives imagery detailed enough to show crater patterns clearly. For many of the others, science begins with orbit before it reaches surface. That may sound limited, but orbit itself is revealing here. The way these moons are arranged tells a story about formation, disruption, and survival. Their paths indicate that Uranus likely does not preserve an untouched primordial inner system. Instead, this appears to be a zone where bodies have been broken, reassembled, and sorted repeatedly, with the current moons representing the latest long-lived pattern rather than the first one. Their darkness adds to that impression. Compared with some brighter icy moons elsewhere in the solar system, the inner moons of Uranus appear subdued and low in reflectivity. They do not shine strongly. They absorb light and reveal little from a distance. Yet that visual restraint is part of their importance. Uranus keeps, in a compressed space near the planet, a record of how small moons can coexist with dust, how shepherding can maintain narrow structures, and how closely packed orbits can remain orderly for long intervals while still drifting toward future change. So this inner moon architecture is not a simple ladder leading inward. It is a crowded orbital workshop made of dark minor bodies, each moving in weak sunlight around a sideways planet. Some hold nearby material in place. Some may feed dusty structures. Some belong to a compact cluster that may not be permanently stable. All of them show that the region just outside the rings is one of the most intricate parts of the Uranian system. The outer moons present cold individuality. The inner moons present relationship. Each one matters less as an isolated world than as part of a tightly arranged ensemble whose structure depends on spacing, gravity, and time. Beyond the crowded inner moons, Uranus is surrounded by faint ring material that does not resemble the bright broad rings often imagined around a giant planet. These outer rings are delicate, dusty, and difficult to see. They do not announce themselves with strong reflected light. Instead, they appear as restrained structures, spread thinly through space and revealed only by careful observation. Their importance lies partly in that faintness. They show that the ring system of Uranus is not made only of narrow dark bands. It also includes wider and more diffuse material, held in orbit under weak sunlight and shaped by a close relationship with very small moons. The outer rings are broad rather than sharply confined, and they are dominated by dust. Dust means tiny solid particles, much smaller than the larger chunks thought to make up denser ring components elsewhere in the system. This fine material scatters light in a different way. It can make a ring appear soft at the edges, low in brightness, and difficult to separate from the darkness around it. A dusty ring is better understood as a loose cloud of orbiting grains, all travelling around the planet together but spread across a wider zone. Observations identify two especially important outer dusty rings. One lies closer to the planet and is usually called the New Ring. The other lies farther out and is known as the Mu Ring. Both are much fainter than the more concentrated ring structures long known from stellar occultations and from the Voyager 2 encounter. Their discovery in the early 21st century showed that Uranus keeps more than a single style of ring material. The planet supports narrow, dark structures, but it also supports these wider dusty bands whose existence becomes clear only when telescopes are sensitive enough to collect extremely faint light. This alone changes the picture of Uranus. The ring system is not simple. The New Ring occupies a broad region associated with the inner moon group, and it appears slightly red in colour. That colour description is not a vivid human red. It means only that the ring reflects relatively more longer wavelength light than shorter wavelength light when measured carefully. Such colouring suggests particle properties different from those in the bluer outer ring. The exact composition remains uncertain, but observations indicate that the grains are dark and processed, not fresh, bright ice spread cleanly through space. The New Ring seems to belong to the same muted visual world as many of the nearby small moons. It is faint, dusty, and quiet, yet clearly present as part of the outer ring architecture. Farther out lies the Mu Ring, which is broader and in some observations appears blue. Here again, blue does not mean bright or saturated colour in an ordinary visual sense. It means that the ring scatters shorter wavelength light more effectively. In planetary rings, this can happen when the dust is dominated by very small particles. The Mu Ring has therefore drawn attention because its light-scattering behaviour resembles that of other dusty rings in the solar system, where small grains are being continually supplied. The tiny moon Mab orbits within this region, and is widely considered the most likely source of much of the ring's dust. Impacts by micrometeoroids can strike the surface of a small moon and eject fine material into orbit. Over time, repeated impacts can replenish a dusty ring that would otherwise lose particles. This idea matters because dust is difficult to keep forever. Small grains are vulnerable to many influences. Sunlight, even weak sunlight at Uranus, can alter their motion slowly. Electromagnetic effects can matter because Uranus has a strange magnetic environment. Collisions between particles can grind material down further or move it into slightly different paths. Some dust falls inward, some escapes, and some is swept up again by moons. A dusty ring is therefore not best imagined as a permanent fixed object. It is more like a maintained condition. As long as fresh grains continue to enter orbit, the ring persists. In this region, moons and rings cannot be treated as separate subjects. The rings are related to them physically. The broad dusty ring associated with Mab is the clearest example. The nearer dusty ring also occupies a zone populated by small inner moons, and its material may likewise be linked to impacts and debris exchange within that compact satellite environment. This creates a picture of Uranus, in which small bodies and fine particles exist together in a continuous system. A moon is struck, dust is released, grains spread along similar orbits, and a faint ring becomes visible. The ring then records not a single event but the repeated small violence of impacts accumulated over long spans of time. The colours of these rings are especially revealing because Uranus is usually thought of as a visually uniform world of blue-green restraint. Its outer ring region quietly complicates that impression. One dusty band appears redder, another appears bluer. These differences suggest differences in particle size, composition, or both. Nearby moons may contribute different debris. Different grain sizes may survive better in different places. The ring system thus becomes a subtle laboratory of light and matter, where faint colour distinctions carry physical meaning. These outer dusty rings extend the remoteness of Uranus into structure. They do not form a bold frame around the planet. They hover as thin traces, easy to miss and difficult to hold in the mind. This faintness is not emptiness. It is a sign of low-density order, of material spread so sparingly that the system must be studied with patience. So the outer ring region around Uranus is a zone of dust, breadth, and continual renewal. It contains broad, faint bands rather than only compact dark structures. It contains colour differences that point to differences in the particles themselves. It contains strong ties between tiny moons and the material orbiting near them. Observations indicate that the rings persist because they are fed, thinned, and fed again, all within the calm-looking outer reaches of the Uranian system. Nothing here appears dramatic at first sight. Yet this is one of the clearest signs that Uranus supports a ring environment more varied than its distant appearance suggests. In weak sunlight around a sideways planet, fine grains continue their silent circuit, making a ring system that is not bright, not simple, and not still. Inside the faint dusty bands, the ring system of Uranus becomes narrower, darker, and more sharply defined. These are the main rings, the structures that first revealed that Uranus is surrounded by something more precise than a loose veil of orbiting material. They are not broad, luminous sheets like the rings of Saturn. They are mostly slender, dark grey bands, confined to a compact region close to the planet. Modern observations describe 9 of them as the main rings, with names that include alpha, beta, eta, gamma, delta, lambda, and epsilon. Together with the inner members of the closely packed set nearer the planet, their visual character is restraint. They reflect little light, occupy surprisingly narrow paths, and seem built not for display but for persistence. The discovery of these rings came not first through ordinary imaging, but through a more delicate method. In the 1970s, astronomers watched Uranus pass in front of a distant star and noticed repeated brief dips in the star's light before and after the planet itself crossed the line of sight. Those dimmings showed that narrow rings were blocking the starlight. This was an important clue to the nature of the system from the very beginning. The rings were not diffuse enough to cause a broad fading. They are concentrated enough to produce a sequence of distinct interruptions. Later observations from Earth added more rings, and Voyager 2 confirmed and extended the picture during its flyby in the 1980s. From the start, the ring system of Uranus presented itself as compact, narrow, and unexpectedly exact. Their darkness remains one of their most striking features. Early measurements and imaging showed that the particles in the Uranian rings are darker than those in the brighter ring systems familiar elsewhere. This means they reflect very little of the sunlight that reaches them. Under the already weak illumination of the outer solar system, that low reflectivity makes them especially subdued. Instead of surrounding the planet with brilliance, they outline it with barely visible restraint. A ring can be scientifically important without being visually grand, and Uranus demonstrates that clearly. The main rings form a system that is difficult to see well, precisely because the material is so dark. That darkness also helps explain why Uranus differs so strongly from Saturn in the popular imagination. Saturn's rings are wide, bright, and dominated by water ice that reflects sunlight efficiently. Uranus offers almost the opposite impression, Its main rings are narrow rather than expansive, dim rather than radiant, and visually severe rather than ornate. The contrast is not merely aesthetic. It points to different particle properties, different dynamical histories, and different balances between large chunks, fine dust, and external processing. The main Uranian rings appear to contain a relatively low amount of dust overall compared with the faint dusty bands discussed farther out. Much of the ring mass is thought to reside in larger bodies and clumps, while belts of fine dust surround some of the denser rings. This makes the main ring region feel hard-edged. The narrow bands are not simply dust clouds, they are more confined structures, with sharper boundaries and stronger internal concentration. The epsilon ring stands out above the rest. It is the brightest and densest of the main rings and accounts for much of the light reflected by the Uranian ring system. Even this brightest ring remains modest by the standards of Saturn, but within the Uranian family it is dominant. Its brightness is not uniform in all circumstances because the ring is not perfectly circular. Variations in width and particle crowding affect how much light it reflects. What matters most here is that the epsilon ring serves as the clearest example of how narrow and concentrated the main rings can be. It is a confined band, not a broad disk, and its very existence depends on the maintenance of a sharply defined orbiting structure close to the planet. The other main rings continue this same disciplined architecture. They lie in a tight stack, one inside another, each occupying its own orbital lane. Some are only a few kilometers wide. Several are accompanied by diffuse dust belts or faint shoulders that spread away from the denser core. But the overall impression remains one of narrow confinement. The system is therefore not smooth. It is segmented. Empty or relatively empty gaps separate denser bands, and the planet's ring region becomes a study in spacing. Matter is present, but only in specific allowed paths. The sharpness of these divisions suggests that the rings are not free to drift outward or inward without constraint. Something in the local gravitational environment preserves narrow zones of stability while leaving nearby regions comparatively depleted. This sharp confinement is one reason the main rings have long been linked to nearby moons and to unseen small bodies. Gravitational guidance from moons can keep ring particles gathered and prevent a dense ring from diffusing away over time. In the case of the epsilon ring, Cordelia and Ophelia act as shepherd moons, helping hold the ring in place from either side. In other parts of the system, wave-like structures and edge disturbances have suggested that tiny moonlets may also influence ring form, although not all such bodies have been directly observed. Observations therefore indicate that the main rings are not isolated bands of matter left entirely to themselves. They are part of a controlled orbital environment in which nearby gravitational partners help maintain narrow structure. The origin of the rings is less certain than their present shape. Many scientists infer that they are relatively young compared with the age of the solar system, and may be debris from disrupted moons or from repeated collisions among small bodies. The main support for this view is the combination of their darkness, their confinement, and the expectation that such a narrow system is easier to preserve over shorter timescales than over the full history of the solar system without change. It remains uncertain exactly which events created the present rings, or how many earlier generations of moons and debris may have come before them. What is clear is that the system now visible is the product of breakage, survival, and orbital sorting rather than a simple untouched remnant from the beginning. So the main rings of Uranus form an inner circle of disciplined darkness. They do not spread widely. They do not shine strongly. They occupy precise lanes close to the planet and hold their form through gravitational order rather than visual abundance. Uranus even here, refuses the easiest comparison. A giant planet can have rings without resembling Saturn. Its ring system can be elegant without being bright. Around Uranus, the main bands are narrow, dark, and exact, a set of orbiting structures whose quiet severity fits the character of the planet itself. Under weak sunlight, close to a sideways world, these rings draw a fine, restrained boundary that is easy to overlook from afar and impossible to ignore once understood. At the top of Uranus, before attention reaches the deeper clouds or the stronger motions below, there is a quiet, visible layer of haze. This is the first true atmospheric face of the planet. From far away it gives Uranus its smooth appearance, softening contrast and muting detail across the globe. The eye does not immediately meet sharply banded weather or deep color variation. It meets a subdued outer veil, a high atmospheric layer that scatters light and makes the planet appear calm. That calmness is real in appearance, but it is not emptiness. The upper atmosphere contains structure, and that structure changes with season. A haze is made of very small particles suspended in the atmosphere. On Uranus, these particles form high above the deeper visible cloud layers. They do not create a hard surface or a sharply defined shell. Instead, they make a broad diffuse region through which sunlight passes, reflects, and scatters before leaving the planet again. The effect is subtle but powerful. Fine haze reduces the visibility of whatever lies below it. It turns stronger atmospheric contrast into gentler tonal change. This is one reason Uranus looks smoother than Jupiter, and often smoother than Neptune. The upper haze acts like a veil, effective enough to soften its face. The composition of this upper haze is linked to the chemistry of the Uranian atmosphere, and to the weak sunlight received in the outer solar system. Methane gas higher in the atmosphere absorbs red light strongly, leaving reflected light richer in blue and green tones. At the same time, the haze particles scatter sunlight in ways that further shape the pale blue-green appearance seen from a distance. The visible colour of Uranus therefore comes from light passing through an atmospheric column where gas and suspended particles both influence what is reflected outward. Within this high haze, one of the most important large-scale features is the polar hood. This is a brightened cap-like region that forms over a pole during the long approach to summer sunlight. It does not appear as a solid cap in the way ice covers a planetary surface. Uranus has no solid visible surface at this level. The polar hood is instead a broad atmospheric brightening, produced by changes in the upper haze and cloud structure under long seasonal illumination. Observations over recent decades show that the northern polar region becomes brighter as Uranus moves through the part of its 84-year orbit that brings increasing sunlight to that hemisphere. This bright polar area is one of the clearest signs that Uranus responds to season in its visible upper atmosphere. Since each season lasts about 21 Earth years, the response is slow. There is no quick annual cycle of the kind known on Earth. Instead, the polar hood develops gradually over many years. Telescopes observe it growing in brightness and extent as the hemisphere receives longer sustained illumination. The process is not instantaneous because the atmosphere of Uranus changes on long radiative timescales. Radiative means link to the gain and loss of energy through light. In a cold giant atmosphere far from the Sun, even modest changes in solar heating can take years to alter temperature structure, haze formation, and the appearance of broad regions. The hood also shows that sunlight matters at Uranus, even though the Sun is weak there. The planet receives only a small fraction of the sunlight that Earth does. Yet that small fraction still guides visible atmospheric change when applied steadily over decades. A hemisphere held in long seasonal light does not remain identical to one that has turned away into long darkness. The upper haze responds. Particles may become more or less abundant, and the vertical layering of the atmosphere may shift in a way that changes how light is scattered back to space. Observations indicate that seasonal illumination is strongly connected to these polar brightening patterns, even if the exact process that produces every detail remains uncertain. The appearance of the polar hood also helps explain why Uranus can seem to change character over time while still preserving its general calm. In some years, the planet presents a relatively plain disk with little obvious contrast. In other years, especially with modern high-resolution observation, the polar region stands out more strongly as a bright cap-like feature. This does not mean Uranus becomes visually violent. It means the upper atmosphere changes its emphasis. The planet remains subdued, but not fixed. Its most visible long-term transformation is written in the slow reorganization of high haze over a pole. This upper layer is important because it defines the first boundary between space and the deeper atmospheric world below. Incoming sunlight meets the haze before it meets the lower visible cloud structure. Outgoing reflected light is shaped by the haze before it leaves the planet for distant observers and instruments. The upper atmosphere therefore acts as a filter. It does not generate all visible features, but it controls how clearly they can be seen. A thicker or brighter high haze can conceal contrast below. A thinner or differently structured haze can allow more detail to emerge. The polar hood is also a reminder that Uranus does not break rules by ignoring physical law. It breaks expectation by using familiar law under unfamiliar geometry. A planet tilted almost on its side receives sunlight in a pattern unlike that of other major planets. A cold atmosphere with methane and haze responds over long spans of time. A bright polar hood emerges as the visible record of that long seasonal forcing. So the first atmospheric region of Uranus is a pale outer veil shaped by gas, particles, and patient sunlight. It smooths the appearance of the globe, softens contrast, and gives the planet its restrained visible face. Over the pole that turns into long summer light, the haze brightens into a broad hood that can be traced across years of observation. Here, at the top of the atmosphere, Uranus begins to show how a remote cold giant can still change in visible ways. Its upper haze is quiet, but it is not still. Its polar brightening is gentle, but it is real. And together they form the first atmospheric expression of a planet whose seasons last decades and whose outer face is written in light filtered through a high cold veil. Below the high haze and within the first clearly reflective level of the atmosphere, Uranus shows the region that gives the planet its familiar colour. This is the zone of the visible cloud tops, the broad upper layer from which much of the sunlight that reaches Uranus is reflected back into space. The planet appears blue-green not because its clouds are naturally painted in those colours, but because light is altered as it passes through the gases above and within this upper atmospheric region. The visible face of Uranus is therefore a record of atmospheric filtering. Sunlight arrives white, containing many colours together. By the time part of it leaves the planet again, some colours have been removed more effectively than others. What remains is the pale blue-green light that gives Uranus its quiet, cool appearance. The main gases in the upper atmosphere are hydrogen and helium, with a smaller but crucial amount of methane. Methane is the key to the planet's colour. It absorbs red wavelengths of sunlight strongly. When sunlight enters the atmosphere of Uranus and reaches the levels where clouds and haze scatter it back outward, much of the red part has already been taken out by methane. Blue and green wavelengths are left to be reflected more efficiently towards space. This is why Uranus does not look white, grey, or yellow. Its colour is the visible result of methane removing one part of sunlight and leaving the rest behind. That blue-green colour is often described as uniform, and from a great distance it does appear smooth and nearly even across the disk. Yet the apparent simplicity hides a layered process. Light does not simply strike a solid top and return. It moves downward through gas, encounters haze and cloud particles and scatters, and then travels outward again through the same absorbing atmosphere. Each passage through methane changes the balance of colours. Each encounter with aerosols, meaning tiny suspended particles, softens contrast and modifies brightness. Uranus therefore looks calm because its atmosphere acts as a filter as much as a reflector. The eye sees a broad even globe, but the atmosphere creates that evenness by blending what would otherwise appear more varied. The visible cloud tops themselves are not a solid boundary. They are the highest major reflective cloud region that can usually be sensed in ordinary visible light. At this level, the atmosphere is cold enough for methane to condense into cloud particles in certain layers and locations. These cloud particles help send sunlight back outward. In some images they remain difficult to separate from the surrounding haze, which is one reason Uranus long appeared nearly featureless in visible observations. Voyager 2 saw a subdued blue-green world with very little obvious detail. Later telescopes, especially when observing in selected wavelengths, reveal that the apparent plainness does not mean absence of structure. It means the upper atmosphere conceals and softens much of what lies within it. This helps explain one of the quiet differences between Uranus and Neptune. Both planets contain methane in their upper atmospheres, and both therefore absorb red light and appear blue. Yet Uranus usually looks paler and more washed with green than Neptune. Observations indicate that this is connected not simply to methane itself, but also to the thickness and behaviour of the haze above the deeper reflective layers. A thicker haze on Uranus appears to whiten the colour somewhat, muting the deeper blue that would otherwise be seen more strongly. In that sense, the blue-green cloud tops of Uranus are the result of two atmospheric influences working together. Methane creates the basic colour by removing red light. The haze softens and lightens that colour into the quieter tone that observers know. Even where the colour seems almost the same across the globe, subtle changes matter. Modern observations show that methane is not always distributed evenly at all latitudes. Some polar regions are more depleted in methane than other parts of the upper atmosphere. This does not overturn the basic explanation of colour, but it adds refinement. The visible appearance of Uranus is not created by a single perfectly mixed layer. It emerges from an atmosphere in which methane abundance, haze thickness, and cloud reflectivity vary with place and season. As a result, some regions appear slightly brighter or less blue-green than others. These differences are usually gentle rather than dramatic, yet they are physically meaningful. They show that the calm face of Uranus is produced by structure, not by sameness. The cloud tops also reveal how Uranus can seem quiet while still remaining active as a planet. The visible atmosphere presents a restrained surface of light, one in which broad colour fields matter more than sharp contrast. This does not mean the cloud region is static. It means that most of its changes are subtle at the level first seen by ordinary observation. The cloud tops reflect sunlight through a veil of gas and haze, so the planet's visible face becomes one of muted distinctions. Brightness shifts, faint patches, and broad polar changes can be present without breaking the overall stillness of the globe. There's also a deeper lesson in this coloured upper layer. A planet very far from the Sun can still be recognisable through atmospheric chemistry alone. Uranus does not need intense sunlight to create a distinct appearance. Even weak sunlight, when filtered through methane and reflected by cloud particles, becomes enough to produce one of the solar system's most characteristic planetary colours. The blue-green face of Uranus is therefore not decoration, it is chemistry made visible. It is a sign that the atmosphere contains specific gases in specific layers, and that light is forced to pass through them before returning to space. So this region of Uranus is defined by reflected light and selective absorption. The upper cloud tops provide the reflecting surface, though not a solid one. Methane removes the red from sunlight. Haze softens the result into a pale, even, blue-green world. Slight regional differences in methane and aerosols give the disk gentle variation without disturbing its overall calm. This is the first deep atmospheric identity of Uranus, after the outer haze, a planet whose colour comes from the quiet discipline of chemistry, whose clouds shine through filtered light, and whose visible face appears simple only because its atmosphere blends complexity into one smooth and memorable tone. Within the visible upper atmosphere of Uranus, motion begins to show itself more clearly. The planet often appears calm when seen as a whole, yet that calm is not the same as stillness. Clouds drift, bright features form and fade, and winds move the atmosphere around the globe with considerable speed. This region is where Uranus stops looking like a nearly uniform-coloured sphere and begins to reveal itself as a world with weather. The weather is not constant in display. It is intermittent, subtle at times, and easier to detect in some wavelength than in others. But it is real, and it shows that the atmosphere is active even when the planet seems quiet from afar. Wind in a giant planet atmosphere means large-scale horizontal motion of gas. There is no solid surface beneath these winds to interrupt them in the way mountains, plains, and oceans shape the atmosphere of Earth. On Uranus, winds move through broad belts and zones that circle the planet at different latitudes. Measurements made by tracking clouds show that the speed and direction of these winds vary with latitude. Some latitudes move faster than others, and the pattern is not perfectly symmetrical between north and south. This creates a circulation system that is structured rather than random. The atmosphere does not simply drift in one universal direction. It is divided into bands of motion. These winds can be very fast. Observations indicate that some cloud features move through the upper atmosphere at speeds of several hundred kilometers per hour, and in some cases around or above 900 kilometers per hour. Such winds do not always reveal themselves through obvious turbulence in ordinary images, because Uranus is blanketed by haze and because many cloud contrasts are faint. The atmosphere can keep a smooth outward appearance even while air moves rapidly within it. This is one of the quiet lessons of Uranus. A planet does not need dramatic striping to possess powerful winds. Motion can be strong while visibility remains subdued. The winds become easier to understand when bright discrete clouds are present. A discrete cloud is a separate visible feature rather than part of a continuous band. On Uranus, these clouds are often made of methane ice crystals that condense when air rises and cools. Rising motion matters because a gas that expands in lower pressure cools, and when it cools enough, methane can condense into fine particles. Those particles reflect sunlight efficiently and appear as bright spots or patches against the softer background atmosphere. In this way, a storm or an upwelling becomes visible. What is seen is not the wind itself, but a cloud created by motion. These bright cloud features can be small and short-lived, or they can become large enough to draw attention even in global images of the planet. Modern observations with large telescopes and the Hubble Space Telescope show that Uranus can produce multiple bright storms at mid-northern latitudes, especially as the northern hemisphere moves deeper into its long summer season. Some appear near the edge of the bright polar hood, others emerge farther from the pole. They can drift with the prevailing winds, change shape, brighten, weaken, and disappear. Their presence makes clear that the upper atmosphere is not a fixed sheet of colour. It is a place where local vertical motion interrupts the broader smoothness and briefly leaves bright marks on the globe. Not all storm features on Uranus are simply isolated bright clouds. At times, darker vortices and their associated bright companion clouds have also been inferred or observed. Though they are more difficult to study than similar features on Neptune, a vortex is a rotating atmospheric structure, a broad spinning region within the flow. If surrounding air is forced upward around such a disturbance, methane clouds can form nearby and become visible even when the darker circulation itself is harder to detect. This means some of the bright activity in the atmosphere may be linked not only to local convection, meaning rising and sinking motion, but also to larger organized structures embedded in the winds. The seasonal setting seems to matter. Uranus receives weak sunlight, yet it receives it in an extremely uneven pattern over time because of its sideways tilt. As the North Polar region approaches summer, observations show a thickened polar haze and an increasing number of small storms around the boundary of that bright cap. This does not mean sunlight alone explains every cloud. The atmosphere also responds to internal heat flow, chemistry, and circulation. But the timing of observed changes indicates that season influences where visible activity becomes easiest to detect. Uranus therefore does not have weather in spite of its long seasons. It has weather shaped by them. One of the most striking aspects of this region is the contrast between expectation and evidence. Voyager 2 passed Uranus during a time when the planet looked unusually bland, and for years that encounter helped establish the image of Uranus as a nearly featureless world. Later observations changed that picture. As viewing conditions improved and as seasons shifted, more clouds and more signs of activity became visible. The planet did not suddenly become active. It became easier to see that activity was present. This distinction matters. Uranus is not a dead atmosphere that occasionally wakes. It is an atmosphere whose visible expression depends strongly on season, wavelength, and patience in observation. The storms themselves remain modest in shape compared with the most famous giant storms elsewhere in the solar system, but they are significant because they interrupt the planet's long reputation for stillness. They show that methane can condense into bright clouds. That air can rise forcefully enough to create visible contrast, and that broad winds can carry these features through the atmosphere once they form. Each storm is therefore both an event and a tracer. It is a local weather phenomenon, and it is also a marker that lets scientists measure motion in the surrounding air. So this atmospheric region of Uranus is one of restrained movement made visible by clouds. Winds race through broad latitude bands. Methane condenses in rising air and creates bright, discrete features. Small storms gather, drift, and fade against a background that still appears calm at first glance. The upper atmosphere does not display its energy constantly, but when cloud features emerge, they reveal a world that is quietly dynamic. Uranus remains pale, smooth, and distant in overall appearance, yet within that pale face the winds continue, the storms appear, and the atmosphere carries on with motions powerful enough to reshape what observers can see from one season to the next. Below the visible cloud tops of Uranus, the atmosphere becomes thicker, darker, and harder to observe directly. This is still atmosphere, not a surface and not yet the deeper planetary body beneath. gas continues downward without a clean boundary, but the conditions change steadily with depth. Pressure rises because more gas lies above. Temperature also rises as sunlight gives way to the planet's own stored heat and to compression. In this region, Uranus is best understood as a layered atmosphere. Each layer is not a rigid shell. Instead, it is a zone in which certain gases, temperatures, and pressures become more important than they are above. The main bulk of the atmosphere remains hydrogen and helium. These light gases dominate the volume of Uranus from the upper visible levels downward through great depth. Mixed into them are smaller amounts of methane, hydrogen sulfide, ammonia, and water-bearing material. Those minor ingredients matter because they control where clouds can form. A cloud layer forms where a gas cools enough, under the local pressure, to condense into droplets or particles. On Uranus, the visible upper atmosphere is linked to methane condensation. Deeper down, other materials are expected to condense in their own zones. The result is not one universal cloud deck, but a sequence of cloud-forming levels arranged by chemistry. The first part of this descent remains close to the levels that produce the clouds tracked in upper atmospheric weather. Pressure there is often discussed in units called bars, a measure of atmospheric pressure. Near the visible methane cloud region, pressure is around 1 to 2 bars. That is already greater than the pressure at sea level on Earth, yet it is still shallow compared with what lies below. In this zone, methane can condense and produce bright clouds when air rises and cools. As the atmosphere deepens, methane becomes less important as the main visible cloud-forming substance. Farther down, the atmosphere shifts toward regions where other chemicals begin to govern condensation. Below the methane cloud level, models and observations indicate a deeper cloud region associated with hydrogen sulfide. Hydrogen sulfide is a sulfur-bearing gas. Its importance was once debated, but observations now indicate that it is a major cloud-forming species in the deeper atmosphere of Uranus and Neptune. In the pressures below the methane cloud layer, hydrogen sulfide is expected to condense into particles and create a deeper cloud deck. This region is not directly seen in ordinary images because the higher haze and methane layers block a clear view. Yet its existence helps explain why the atmosphere is chemically layered, rather than mixed into one transparent volume. The role of ammonia is more uncertain in the accessible upper part of Uranus than it is on Jupiter or Saturn. On those planets, ammonia is a familiar cloud-forming gas high in the atmosphere. Uranus appears different. Observations suggest that ammonia is less abundant in the upper accessible layers, perhaps because it is tied up deeper down or removed through chemical processes and cloud formation at greater depth. That means the atmosphere of Uranus does not reproduce the same neat sequence often used to describe Jupiter. The broad idea of layered condensation still holds, but the exact vertical abundance of each gas and the depth at which it becomes well mixed remain incompletely measured. No probe has yet descended through the Uranian atmosphere to sample these levels directly. Much of what is known comes from spectroscopy, laboratory physics, and atmospheric models. As the descent continues, the atmosphere becomes denser and less transparent. Sunlight can no longer penetrate effectively. The region passes from one that can be interpreted through reflected light into one where understanding comes mainly from physics. Temperature rises further. Pressure rises from a few bars to tens of bars and then beyond. Under such conditions, gases that behave simply in thin upper air begin to interact in more compressed ways. Convection, meaning the upward and downward transport of heat by moving material, may still occur, but it can be modified by composition. If one layer contains a different concentration of condensing material than another, vertical motion may be hindered or redirected. In this way, chemistry can influence circulation, and circulation can influence where clouds actually form. This deeper atmospheric layering may also help explain one of Uranus's long-standing puzzles, its muted outward appearance and weak excess heat compared with Neptune. Observations show that Uranus emits only a small amount of internal heat beyond what it receives from the Sun. One possibility is that some part of the atmosphere and upper interior is stably layered, meaning that material of different composition resists large-scale overturning. If mixing is limited, heat from below may not rise as efficiently toward the upper atmosphere. The exact structure responsible remains uncertain, but the idea fits the broader picture of Uranus as a planet whose layers are not freely blended. Water is expected to become important much deeper than the levels directly sensed by telescopes. Under the temperatures and pressures of the upper and middle atmosphere, water does not dominate the visible cloud region. It belongs to far deeper atmospheric levels where the air is warmer and much more compressed. Scientists therefore infer a very deep water cloud layer or water-rich region below the hydrogen, sulfide and methane zones, but they cannot yet describe it from direct measurement. The upper atmosphere can be seen. The lower atmosphere must often be inferred. Between the two lies a large vertical range in which temperature, pressure, and chemistry all shift continuously. So the deeper atmosphere beneath the visible cloud tops is not an empty descent into featureless gas. It is a structured column. Methane clouds belong to the shallower visible levels. Hydrogen sulfide likely condenses deeper down. Ammonia remains harder to trace and may stay hidden at greater depth than once expected. Water lies deeper still, in conditions beyond present direct reach. Through all of this, pressure and temperature increase steadily, while the atmosphere becomes denser and darker. Uranus keeps no hard surface to mark a simple end to weather. Instead, it offers a gradual thickening world in which each deeper level changes the rules of cloud formation. The smooth blue-green face seen from far away is only the top expression of a much more layered atmospheric body, one that descends through chemistry, compression, and fading light into regions that are still air, yet already very different from the sky above. Below the deepest atmospheric cloud regions, Uranus enters a domain that is no longer well described as ordinary sky. The descent has passed beyond the levels where visible clouds form and where sunlight can still influence appearance. Pressure has risen so greatly and temperature has increased so steadily that the materials present begin to behave in unfamiliar ways. This is the middle depth of Uranus, the region often described in planetary science as rich in water, ammonia, and methane under immense compression. The word ice in the phrase ice giant comes from this level of understanding. It does not mean that Uranus contains vast simple blocks of frozen material like a winter landscape. It means that substances which would be called ices in the cold of space, such as water, ammonia, and methane, are major ingredients of the planet's deeper body. Here they do not remain ordinary ice. They're compressed, heated, and transformed into dense planetary matter. This region is important because it distinguishes Uranus from Jupiter and Saturn. All four giant planets contain large amounts of hydrogen and helium, but Uranus and Neptune are enriched in these heavier volatile substances to a much greater degree. Volatile here means a substance that easily becomes gas under many conditions found in planetary environments. In the outer solar system, water, ammonia, and methane are counted among the major volatile compounds. During the formation of Uranus, such materials were likely abundant in the cold outer protoplanetary disk, and a substantial share of them became part of the growing planet. As a result, beneath the relatively shallow hydrogen and helium atmosphere lies a much larger fraction of dense material than is present in the larger gas giants. At these middle depths, the distinction between gas, liquid, and solid becomes less useful in the everyday sense. Pressure is too high and temperature too elevated for simple familiar states to apply. Water may exist not as ordinary liquid water and not as ordinary ice, but as a hot compressed fluid. Ammonia and methane also become part of dense mixtures that may blend, separate, or react depending on the exact pressure and temperature. Scientists often speak of an ionic fluid in such regions. Ionic means that atoms within the material can lose or gain electrons, allowing electric charge to move more freely than it would in an ordinary molecular fluid. Under enough pressure, water and ammonia can break into electrically active forms, and this may matter greatly for the magnetic behavior of the planet. These middle depths are therefore not only chemically rich, they are physically strange. A person accustomed to thinking of water as something that freezes, melts, or boils under familiar conditions must leave that intuition behind here. Deep inside Uranus, water-bearing material may become a dense hot fluid capable of conducting electricity. Methane may break apart under pressure. Carbon could in principle separate from hydrogen in ways that have led to discussion of diamond formation at great depth, though the extent and exact location of such processes remain uncertain. What is secure is the broad picture. The substances associated with ice in a cold outer solar system setting do not remain simple icy matter inside Uranus. They are forced into high-pressure forms that belong to planetary interiors rather than to ordinary experience. This helps explain why the middle depth of Uranus is often described as a mantle, though the word must be used carefully. On Earth, mantle means a rocky layer between crust and core. On Uranus, it refers instead to a vast surrounding region of compressed volatile-rich material beneath the outer hydrogen and helium envelope. The comparison is structural rather than compositional. It marks a middle planetary zone, not a rocky one. This zone likely contains most of the planet's mass and occupies much of its interior volume. It is not a thin layer, it is the dominant body of Uranus beneath the atmosphere that can be sensed from above. The behavior of this region may also help explain the unusual magnetic field of Uranus. A planetary magnetic field is generated when electrically conducting material moves in an organized way. On Earth, this happens deep in the molten metallic outer core. On Jupiter, conductive hydrogen plays the central role at great depth. Uranus appears different. The tilt and offset of its magnetic field suggests that the field may be generated not near a simple central core, but in a shell of conducting fluid located farther outward. The compressed water-ammonia region is a leading candidate for that shell. If part of this volatile-rich mantle becomes electrically conducting and convects, meaning that hot material rises while cooler material sinks, then it can generate a magnetic field. Because the generating region may sit in an outer shell rather than a deep-centered core, the resulting magnetic geometry can be more irregular. In this way, the chemistry and physics of the middle depths may help produce one of the most outwardly strange properties of Uranus. Yet this region is not directly observed. No spacecraft has descended into it. No probe has sampled its composition in place. Scientists infer its existence from the mass, size, gravity, magnetic field, and atmospheric composition of the planet, together with laboratory studies of matter under extreme pressure. This means the broad outline is strong, while many details remain open. Observations indicate that Uranus must contain a large fraction of heavy volatile material beneath its hydrogen-helium envelope. It remains uncertain exactly how sharply the layers are separated, how mixed the materials are, and how temperature changes with depth through this immense zone. Some models suggest relatively smooth transitions. Others suggest compositional gradients, meaning that material changes gradually enough to resist large overturning motion. That last point matters because this middle depth may not be freely stirred from top to bottom. If one layer contains slightly different proportions of water, ammonia, methane, and hydrogen than the layer above it, then buoyancy can be suppressed. Buoyancy is the tendency of warmer or lighter material to rise. When composition changes in the same direction as temperature, layers can remain stably arranged even if they are hot below and cooler above. This would make it harder for heat to escape efficiently upward. Uranus, which emits only a small excess of internal heat compared with Neptune, may preserve exactly this kind of quiet, deep structure. The volatile, rich middle region could therefore be both the defining body of the planet and part of the reason it appears so thermally subdued. So the middle depths of Uranus are a realm of compressed volatiles, not of ordinary air and not yet of the deepest central interior. Water, ammonia, and methane dominate the identity of the region, but they do so in transformed forms shaped by enormous pressure and rising temperature. The word ice points to their origin in cold outer solar system chemistry, not to their present physical state. Here they become dense fluids, possibly electrically conducting, occupying a vast inner mantle that likely governs much of the planet's magnetic and thermal character. Uranus is called an ice giant because of this region more than any other. Beneath its pale atmosphere lies a huge body of strange, hot, compressed matter made from substances that begin as simple outer solar system ices and become, under planetary force, something far more complex. Deep within Uranus, beneath the volatile rich middle region and still short of the unseen central center, one puzzle begins to dominate the structure of the planet. Uranus appears to release remarkably little internal heat. Every giant planet receives sunlight from the sun, absorbs part of it, and sends energy back to space as thermal radiation, meaning heat emitted in the form of light beyond ordinary vision. Most giant planets also radiate a noticeable amount of internal heat left over from their formation and from slow contraction over time. Jupiter does this strongly. Saturn does as well. Neptune, though similar in general class to Uranus, also emits much more internal energy than it receives from the Sun. Uranus is different. It gives off only a small excess above the solar energy it absorbs. In outward terms, it is one of the most thermally subdued major planets in the solar system. This matters because a giant planet begins hot. During formation, matter falls together under gravity, and gravitational energy becomes heat. Over time, a planet slowly loses that heat to space. For a world as large as Uranus, some internal energy should still remain after billions of years. The expectation is not that the planet ought to glow fiercely, but that it should release more excess heat than is actually observed. This gap between expectation and measurement is why Uranus has long been considered puzzling. It is not merely cold because it is far from the sun. It is also unusually quiet from within. The measurements themselves do not suggest complete absence of internal heat. Uranus does emit some energy from its interior. The important point is that the amount is small compared with what is seen at Neptune. Since the two planets are similar in size, bulk composition, and outer classification, this contrast is striking. The question is not simply why Uranus is faint in thermal emission. The deeper question is why two apparently related ice giants behave so differently in their internal energy flow. Something in the structure or history of Uranus seems to limit the escape of heat from within. One of the leading ideas is that the deep interior of Uranus may be strongly layered. A layered interior means that material is arranged in zones of differing composition. temperature, or both, in a way that resists large-scale overturning. In many planetary interiors, heat escapes efficiently when warmer material rises and cooler material sinks. This process is called convection. Convection is an effective way to move heat through a fluid region. If Uranus were vigorously convecting through much of its deep interior, heat from below could reach the outer layers more readily and then be lost to space. But if the planet is compositionally stratified, meaning that different depths contain different mixtures of material, then buoyancy may be reduced. A warmer parcel of matter may still fail to rise if it is also denser because of its composition. In that case, convection weakens, and heat becomes trapped more effectively below. This idea fits well with the broader image of Uranus already suggested by its atmosphere and magnetic field. The planet appears to be a world of layers rather than one of simple free mixing. The hydrogen and helium envelope gives way to volatile-rich deeper matter, and within that deeper matter there may be gradual or stepped transitions in composition. A stable interior gradient would act like a barrier to heat transport. Instead of rising in broad overturning motions, heat would have to leak outward more slowly by conduction or by limited local mixing. Conduction is the transfer of heat through matter without bulk movement. It is less efficient than strong convection over planetary scales. A deeply stratified Uranus would therefore cool outward only slowly, preserving heat below while revealing little of it above. Another possibility is that Uranus experienced a violent event early in its history that changed the way its interior evolves. Giant impacts have long been considered in relation to the planet's extreme tilt, and such an event could also have rearranged internal layers. A sufficiently energetic collision might deposit material in a way that helps produce stable stratification, or separates the planet into regions that do not mix easily afterward. This idea is physically plausible, but the details remain uncertain. Observations strongly support the present thermal quietness of Uranus. They do not yet uniquely identify which past event creates it. The planet may owe its deep structure to formation conditions, later impacts, gradual chemical separation, or some combination of these processes. This hidden thermal character may also help explain why Uranus looks relatively subdued in visible weather compared with Neptune. Neptune, with greater internal heat flux, drives stronger convection and more vigorous atmospheric activity. Uranus can still produce storms and rapid winds, but its overall appearance is often calmer. The connection should not be overstated. Weather depends on many factors, including season, chemistry, and circulation. Still, internal heat is one of the great engines of giant planet meteorology. If Uranus supplies less of that energy upward, a quieter atmospheric expression becomes easier to understand. The muted face of the planet may therefore be linked to a deep thermal restraint that begins far below the visible clouds. The low heat flow also shapes how scientists think about the age and evolution of Uranus. A planet that traps internal heat may not cool in the same way as a more thoroughly convecting world. Its internal temperature profile can remain unusual over immense timescales. Some models even struggle to reproduce the current faint thermal emission of Uranus without assuming barriers to mixing or unusual initial conditions. This is a sign that the problem is not cosmetic. It reaches into the deepest question of how the planet changes through time. Uranus does not simply present a strange present state. It may have followed a different internal history from the one often assumed for giant planets. Yet confidence must be kept within limits. Scientists do not have a direct map of the thermal pathways inside Uranus. They infer them from emitted heat, gravity data, magnetic structure, atmospheric composition, and laboratory knowledge of matter at high pressure. These are strong tools, but they do not produce a single complete answer. Observations indicate that Uranus emits little internal heat and likely contains barriers to efficient deep convection. It remains uncertain exactly how those barriers are arranged, how sharp the compositional layering may be, and how much the present structure reflects ancient impact history rather than gradual internal evolution. So this deep structural region of Uranus is defined less by what can be seen than by what fails to emerge. Heat remains hidden. The planet radiates with unusual restraint. Its interior likely contains layered matter that resists free overturning and slows the escape of energy from below. Uranus, in this sense, breaks expectation not by being active in an obvious way, but by being quiet in a place where more energy might be expected to rise. The result is a giant planet whose silence is itself a physical clue. Beneath the atmosphere and beneath the compressed volatile mantle, deep structure governs the planet by holding warmth back, preserving a long interior stillness that remains one of the most important unresolved facts about Uranus. At the deepest center of Uranus, knowledge becomes most indirect. The planet has no solid surface above, no open descent route for direct observation, and only one spacecraft flyby in all of human exploration. Everything known about the central region comes from the combined reading of gravity, size, mass, rotation, magnetic behavior, atmospheric composition, and the physics of matter under immense pressure. From these clues, scientists infer that Uranus most likely contains a dense central core, probably rich in rocky material and heavier elements, surrounded by the vast compressed mantle of volatile rich matter already traced above it. Yet this inference carries caution. The existence of a deeper dense center is strongly supported. Its exact size, exact composition, and exact boundary with the material above it remain uncertain. Science, NASA, Gov. In simpler planets of ordinary imagination, a core is easy to picture. It is a hard central ball wrapped by clear surrounding layers. Uranus resists that picture. The pressure at depth is so great, and the temperatures so high, that a neat transition from fluid mantle to solid center may not exist in the way familiar from small rocky planets. The core may be partly mixed with the material above it. It may have an extended transition zone instead of a sharp border. If heavier elements are distributed gradually rather than abruptly, then the deepest part of Uranus could be better understood as a concentration of dense material toward the center rather than as a perfectly separate sphere. This is one reason the central region remains difficult to describe in plain visual terms. The language of layers still helps, but the real planet may blur those layers under extreme conditions. Science. NASA. Gov. What can be said with confidence is that Uranus must become denser toward its center. Its total mass is far too large to be explained by hydrogen, helium, water-rich fluids, and methane-bearing mixtures alone without a growing concentration of heavier material at depth. Planet formation theory also supports this view. In the young outer solar system, a growing giant planet is expected to build around an initial accumulation of heavy matter, the solid ingredients that gather before large amounts of gas are retained. Over time, some of that primordial dense material may remain concentrated near the center, even if later mixing redistributes part of it. So the idea of a rocky or rock-rich core is not an arbitrary addition. It fits both the basic mass structure of Uranus and the wider logic of how giant planets form. Science. NASA. Gov. Even so, the word rocky must be used carefully. In the deep interior of Uranus, rock would not resemble ordinary stone. Pressure would alter the structure and behavior of silicates, metals, and other heavy materials just as pressure transforms water, ammonia, and methane above. If a central core exists as a distinct region, it would be hot, compressed, and profoundly unlike any rock body at the surface of Earth. It may contain silicate-rich matter, iron-bearing components, and other heavy elements concentrated under conditions that no direct observation can presently sample. Some models even allow for partial erosion or long-term blending between the core and the volatile mantle. In that case, the deepest region would not be a silent preserved seed from the birth of the planet, but an interior that has evolved along with the rest of Uranus over billions of years. Science. NASA. Gov. The core matters not only because it sits at the center, but because it helps set the conditions for everything above it. The total distribution of mass affects the gravity field. The thermal state of the deepest region influences how heat is stored and how slowly or quickly it can move upward. The chemical relation between the core and the surrounding mantle may help create the stable layering that appears to suppress convection and trap internal energy. If the deepest heavy material remains sharply concentrated, it could support one kind of interior evolution. If it has diffused outward into a gradient, it could support another. Uranus therefore keeps one of its largest unanswered questions in its smallest physical region. The center is hidden, but its arrangement may help explain the planet's weak heat flow, its odd magnetic field geometry, and its overall quietness compared with Neptune. Science. NASA. Gov. This uncertainty is not a failure of planetary science. It is the natural limit of the available evidence. A single flyby by Voyager 2 could measure only part of the gravitational field and only under one encounter geometry. Telescopes can observe the atmosphere and some broad physical properties, but they cannot look through the opaque depths. Laboratory experiments and numerical simulations can reproduce some relevant pressures and temperatures. Yet not every possible chemical combination, and not every planetary timescale. The result is a central model that is strong in outline and flexible in detail. Uranus almost certainly has a dense center. It may be rocky. It may merge gradually into the surrounding volatile-rich interior. It remains uncertain whether it is compact and sharply bounded, partially eroded, compositionally graded, or divided into more than one deep region. Science. NASA. Gov. There is also the possibility that the deepest interior contains phases of matter that do not fit ordinary intuition at all. High-pressure modeling of water-rich and mixed icy compounds suggests that superionic states may occur in ice giant interiors. Superionic means a phase in which one part of the material forms a more fixed lattice, while lighter charged particles move through it more freely, almost like a fluid inside a solid framework. If such phases dominate parts of the deep interior, then the transition from volatile mantle to deepest core becomes even more subtle. Instead of a simple stack of atmosphere, liquid mantle, and rock sphere, Uranus may contain overlapping zones of dense fluid, superionic material, sluggish stratified layers, and a central concentration of the heaviest matter. This is one reason Uranus remains so scientifically important. It is not merely a distant odd planet. It is a natural laboratory for matter under conditions rarely found and never directly touched. Nature. If the center of Uranus could somehow be understood completely, much else about the planet would likely fall into better order. The problem of the weak heat flow would be easier to judge. The origin of the magnetic field would be less uncertain. The history of the tilt might also become clearer if the consequences of ancient impacts for deep layering were better known. Yet at present the deepest region remains one of inference rather than sight. This is fitting for Uranus. From the outer solar system inward, the planet repeatedly appears quiet, smooth, and reserved, while underneath it carries unfamiliar geometry, unusual layering, and hidden physical complexity. The center completes that pattern. It is probably dense, probably rich in rock and heavier elements, and probably not organized in the simplest imaginable way. Beneath the pale atmosphere, beneath the compressed volatile depths, and beneath the trapped internal heat, Uranus likely ends not with certainty, but with a central structure that is only partly resolved and still waiting for closer exploration. Science. NASA, GovNight settles naturally over a subject like this. Uranus remains far away, turning quietly in weak sunlight, holding its long seasons, faint rings, and pale atmosphere without urgency. From the outer darkness around it down to the hidden center within, the planet keeps showing the same calm lesson. A world can seem simple at first sight and still contain deep structure, slow change, and unanswered questions. Its rules are not broken by disorder. They are widened by a different arrangement of the same physics that shapes every planet. The mind can leave the planet now in the same measured way it approached it, moving back outward through haze, through rings, through moons, and into the larger dark where the sun is small and distant. Nothing in Uranus asks for haste. Its year is long, its light is gentle, its secrets unfold slowly, through patient observation and careful thought. Even its mysteries are quiet ones, held in muted colour, in off-centre magnetism, in trapped heat, and in depths that cannot yet be seen. So the planet remains where it has always been, in the cold outer solar system, rolling on its side through an orbit that lasts longer than most human lives. It keeps its reserve, it keeps its distance, and in that distance it offers a steady kind of wonder, one that does not flash or rush, but rests in silence, scale, and the slow persistence of a world that still has more to teach than it has revealed.